Good morning and welcome to the second weekly presentation by our Ghana Chamber of Mines Tertiary Education Fund Awardees. Before we start, I would like to invite Professor Grace Sapon, who is the chairperson for the Ghana Chamber of Mines Tertiary Education Fund Committee on UMAT campus, to give us an opening before we start the presentation. Prof. Hello, Prof.
Hello, Dr. Ziga.
Yes, Prof.
Hello.
Prof, I can hear you.
Hello. You can hear me, all right. Thank you very much, Dr. Ziga, for helping to run this program. Good morning, participants, and you are warmly welcome to the second webinar for the GCM-TEF Research Awardees. Last week, we had a very nice session, and today happens to be the second one. And I believe we are going to enjoy it. For those of you who were on board last week, you agree with me that we learned a lot from those who gave the presentations. And also, we had some good news from the chamber through Madame Laurentia. And even beyond the presentation, we have had some conversations, which shows that we will be able to get a slot during the Chamber's conference, annual conference, so that some of you will get the opportunity to share the beautiful findings that you have from your research. So I see this to be very, very important in the lives of all of us as researchers and in the life of the university, and also a good publicity for the chamber. So this morning, I want to welcome you that we all enjoy the presentations that will come. And this is not going to be the end. It's going to be a weekly thing that will get a chance to listen to the researches that people are doing, our members are doing. So thank you very much, Doc Coordinator.
Thank you, Prof. At this juncture, I would like to invite the first presentation group, who is headed by my own dean, Professor Antonio Wusi. They are going to present on application of hydrogeochemistry, geochemical modeling, and multivariate statistical analysis in identifying geochemical vectors to gold mineralization in the Takoyan group in Ghana. So please, the floor is yours. Thank you.
Thank you very much. My name is Professor Antonio Wusi. I'm the principal investigator, and I'm working with Dr. Jamil Seidu and then Dr. Emmanuel Danuba Sunkari. I'll start with the introduction, and then they will continue with the presentation. But our topic is basically what application of hydrogeochemistry, geochemical modeling, and multivariate statistical analysis in identifying geochemical vectors to gold mineralization in the Takoyan group in Ghana. We've been doing this work for about a year, and what we have done was that we've tried to make some of the software that we have used available to students of the Geological Engineering Department who are part of the Faculty of Geosciences, and most of them have been using this for their project work. If you look at this year, most of the students use some of the software that we have been able to purchase for our work, and then it was a nice presentation by the student. Also, a presentation has already been done at the second biennial research symposium by the Geological Engineering Department. So most of the people in the department are aware of what we are doing. Now we'll start the presentation from the introduction right now to the acknowledgement. So we'll start with the presentation. Yes, the discovery of many surface and near surface deposits has made several exploration companies to now focus on exploring buried and blind target terrains. But the challenges associated with this is very, very, very difficult, and that is resulting in declined exploration successes. And these successless exploration successes are attributed to these challenges. Exploration success in deeply buried and covered terrains is significant to all stakeholders in the mining industry, but this can be very expensive and laborious, because especially when you put in so much money and you are not getting the result that we have. These greenfield sites offer opportunities for new deposit discoveries. For instance, most of the prominent gold belts in Ghana, especially those in the Takoen, are covered by unconsolidated sediments. Therefore, to take advantage of the opportunity and overcome these challenges, gold exploration companies need cost-effective techniques to identify new exploration targets undercover. The slides are not coming. The slides. Alternatively, we can also use geochemical exploration that are being developed to help vector to deeply buried deposits. And we can use geochemistry, biogeochemistry, we can use soil gases and partial soil extractions, and we can use hydrogeochemistry. The advantage of using groundwater as a medium for this gold exploration is that when you have the groundwater coming, it comes from the top and it seeps down to the subsurface. So at least you have all the variance of the chemicals from the top to the down, all buried in the contents of the groundwater. So groundwater undergoes some major reactions with host rocks, and any mineralization, especially under oxic conditions, can be a vector for finding these mineralizations. Yes, these are the associated elements that you can find with the various gold exploration occurrences. If you want to look at magmatic, you have nickel, copper. If you want to look at hydrothermal deposits, you have copper, you have lead. And if you want to look at places, you can have the gold itself, barium, iron, and then thorium. So these are the groundwater conditions that you might have to contain when you have this. And then these are the elements that you'll be looking for. Now, the aim of our project was to use hydrogeochemistry as a tool for identifying gold mineralization in the Takoen group at depth that might be difficult to delineate using superficial exploration techniques like soil and stream sediment geochemistry. The objectives were to determine the geochemical characteristics of groundwater in the area, to determine the degree of rock-water interaction, which will help in developing suitable regional geochemical exploration method for the Takoen system, and to identify pathfinder elements of gold and their geochemical association. And this is very, very important. And also to delineate geochemical anomalies of the pathfinder elements of gold using single and multi-element halo mapping techniques. Nice. Nice. Yes, this is the study area. We are looking at the Takwa area and its environs. And so we are basically looking at the Takoen, where you have the Sunni sandstone, the Dombephilites, Takwa Phyllite, the Banket Formation, the Kawari Group. And on this, we have Gold Fields Ghana Limited, and then Takwa Mine and Ashanti Gold on this same formation. Now, the rocks in this area have basically no primary porosity. So we are looking at secondary porosity that has formed as a result of sharing, fracturing, and then jointing. And the aquifers in this area are normally semi-confined and the unconfined aquifers. So this is the map of the area, and you can see the locations where these samples were picked. We make sure all the samples were picked from the different formations. Now, this is the flow chart of the method that we used. We did our deck study. We did our full data collections. We went to do water sampling. We sent them to a lab for laboratory analysis. And then we look at the major ions, the minor ions, the trace elements, and we also look at gold concentrations. And then we look at multivariate statistical analysis of them. We use that to do our data interpretations, and we drew our conclusion. Currently, we are left with only the petrographic analysis, which we'll do in due course to finish the project. Yes. So these are the results, and then my co-investigator will follow. Hello?
All right, thank you so much, Prof. So one of the objectives was actually to understand the hydrogeochemical characteristics of the water. And so after doing the laboratory analysis, we use box and whisker plot to actually display these particular ions. These are the major ions. And as you can see, sodium is the dominant cation. It has the highest concentration. You see the whisker higher, above the median. Then in terms of the anions, you can see that bicarbonate is the dominant anion in the water because it has the longest whisker above its median. And so this might be due to ion exchange reactions within the aquifer or even carbonate mineral dissolution because we are working in a sedimentary terrain, which is partly metamorphosed. So in terms of the trace elements also, these are mostly related to gold mineralization. So in the water, we realize that iron is a dominant element in the water because this area contains rocks that are iron bearing in nature. And you can see most of the other elements are very low, but look at manganese almost close to the range of iron. And the gold is also having quite a uniform concentration, about 1.0 milligram per liter. And this is what is happening in the aquifer. So in order to also know the water types in the area, because to do this research, you must know the hydrochemical phases. We plotted Piper diagram. And as you can see in this diagram, we have most of the samples plotting in the calcium and then partly in sodium and that of the bicarbonate zone. So that is why about 50% of the water samples have calcium, sodium, bicarbonate chemistry. So the dominant water types are calcium, sodium, bicarbonate waters with other mixed forms. Now, to understand the factors that are controlling the chemistry of the water, we use the Gibbs diagram. And as you can see in this diagram, majority of the samples are plotting in the rock weathering dominance zone. And that tells us that water-rock interaction is actually contributing to the chemistry of the water. And a few samples are plotting in the atmospheric precipitation dominance zone. That suggests that precipitation, which is in the form of rain, may also be contributing to the chemistry of the water. If the rainfall has a particular chemistry and it recharges the aquifer will mimic that chemistry. Now, once we have identified water-rock interaction as the dominant control of the chemistry of the water, that means that there are some ions in the rocks that are dissolving in the water. And there are some minerals dissolving as well. There is some form of exchange of the ions as well. We try to understand that by using bivariate plots. So on the first diagram, as you can see, majority of the samples are on the ion exchange reaction zone. In the second one, the same. That tells us that forward ion exchange reaction predominantly controls the groundwater chemistry. And that means maybe an ion of the same valency is substituting with another ion of the same valency. That's the forward ion exchange. Apart from the ion exchange reaction, we also have some amount of silicate weathering. As you can see, some of the samples are plotting towards the silicate weathering dominant zone, because in this terrain, we have the Brimian also intruding. And so we have silicate minerals like albite and other, silicate minerals. So to some extent, silicate weathering may have also influenced the chemistry of the water. Now let's look at the gold and the major ion relationship. Look at this, we have sodium against gold, and there is a good correlation. That tells us that geochemically, the processes that are enriching sodium in the water are also the same processes enriching gold in the water. It could also be because of some form of alteration, maybe albitization. That might be one of the factors or controls of the gold mobilization in the water. Then when you look at calcium, it's very low. And then when you look at the anions, sulfate and chloride, you can see that sulfate has quite a good correlation with gold as compared to that of chloride. That tells us that sulfate complexing with gold may have resulted in the gold mineralization. Gold is a metal, sulfate is an anion. So sulfate becomes the ligand which carries the gold into the water. Now, we try to also understand the trace element relationships. So in this, with the gold, we can see that iron has a weak correlation with gold. That tells us that the mineralization of gold in the area is not related to iron. But when you look at other elements, for example, arsenic, very good correlation, good moderate correlation. That tells us that arsenic mobilization in the water is related to that of gold. Now, geochemical model saturation indices. We calculated the saturation indices of the various minerals that are showing their signatures in the water. And some of the minerals are dolomite, calcite, we have pyrite, goethite, and hematite. Now, on the first diagram, you can see that all the samples are plotting in the dolomite and calcite under saturation zone. That tells us that in the current hydrogeological conditions, dolomite and calcite are undersaturated. The water is undersaturated with respect to these minerals. Now, what about pyrite? In most terrains where people are exploring for gold, pyrite is always like an indicator mineral. But in where we study, in fact, pyrite is not one because we are not working in an hydrothermal deposit. So you can see that the pyrite saturation indices are very low, negative. That shows that the water is undersaturated with respect to pyrite. Even if pyrite is contributing some amount of control to the water chemistry, it is low. That is why even the correlation coefficient is low. But look at the iron oxide, goethite, and hematite. The water is actually super saturated with respect to these minerals. That tells us that gold mineralization in the Tarquin is associated with iron oxide mineral formation, for example, goethite and hematite. And this is supported by literature, Piguet et al. 2003 and other studies. Now, what kind of environment did the gold form in? So based on the redox potential, the pH, and other parameters of the hydrochemical data, we were able to decipher this. On this first diagram, you can see that the samples are plotting in the oxidizing environment, and that tells us that gold actually mobilized in the groundwater through oxidation reactions, and the environment that it occurred was an oxidizing environment dominated by hematite as the main indicator mineral and not magnetite. Now, which kind of ligand or complexing led to the gold formation? And we can realize that the gold is, the samples are falling within the zone where we have thiosulfide. And that tells us that the gold mobilized in groundwater through thiosulfide complexing instead of chloride or other forms of complexing. And then what about the pH? How does it control the gold in the area? You can see that there is quite a good correlation between pH and gold. That tells us that the pH of the water actually buffers the gold mobilization in the water. Previous studies in other terrains, because this research is, quite new in Ghana. In other places, people have used magnesium number to decipher the type of, mineralization, and then whether the place is not mineralized or not. So in this plot, you will see that areas where we have magnesium number, which is NMG, greater than 0.1, these are the mineralized zones. And where we have magnesium number less than 0.1, those are the non-mineralized zones. What does this tell us? This tells us that leaching of magnesium-enriched gangue minerals like chloride produces groundwaters which constitute a mineralized aquifer signature. And the gangue minerals are also supplying high levels of magnesium, which is expressed as the magnesium number. And where we have higher magnesium number values, then we have what? Mineralized zones. And where we have low magnesium number values, we have non-mineralized zones. So this study results that, or can confirm that the use of magnesium number in the Tarquin as a hydrogeochemical indicator of gold mineralization is possible, and we can extrapolate it to other parts of the Tarquin or other areas. Now, in terms of the statistical analysis, we try to see the inter-element correlations, and our interest here is gold. As you can see, gold shows a good correlation with that of sodium, and that tells us that they were mobilized through the same geochemical processes. But you can see that gold has negative to low correlation with other elements or ions. And this might be because of the degree of metamorphism in the area, which buffered the reactions in the water. And so that is why we are having this kind of disparity. Now, in terms of the multivariate statistical analysis, we use factor analysis to understand the groupings of the elements. And this can actually tell us where gold finds itself and which elements are associated with gold. And they could be deciphered as the pathfinders. So 7 factors were extracted with total variance of 80.91%. And you can see gold is in factor 1. Gold is here associated with lead, arsenic, pH, and magnesium. And this has proven what we said earlier. That shows that these elements, arsenic, lead, magnesium, and the parameter pH control the gold mobilization in the water. Now, to confirm these results, we had to also do hierarchical cluster analysis. In statistical studies, it is better to use several statistical methods to confirm what you've gotten. Now, in using this, a dendrogram was plotted, and it yielded 3 clusters. Cluster 1 is where we find gold, which is our interest. And you can see again, gold is related to iron, arsenic, is related to the element gold itself, nickel, and lead. Out of all these ions and parameters we've seen, these ones I've mentioned are the known pathfinder elements of gold in literature when you go to economic geology or exploration geology. So we can conclude that the pathfinders of gold in this study area could be iron, could be arsenic, could be the element gold itself, could be nickel, and also lead. Now, what are the implications for geochemical vectors of gold mineralization? From in literature to be related to gold mineralization in the Taquin. And now we could see that there was high concentration of iron in the water. And this is actually the signature of these iron oxides. Multi-element correlation, it was indicated that there was some moderate to good correlation of gold with pH, sodium sulfate, and arsenic. And with the multivariate statistics, we had gold associated with majority of the ions and the elements. Therefore, we can confirm that iron, nickel, lead, arsenic, and gold can be regarded as the pathfinders of gold deposits in the Taquin. Now, how do you now explore when you go to the field? Which areas are anomalies, so which is related to the southern domain or southern fringe of the area is where we have gold anomalies. Then for the iron was high in almost all the samples. That's why you have iron spread almost everywhere, but it's within the central and also the eastern parts of the study area. For nickel, we have towards the northeast and then towards the problem we are dealing with. Where can you get the anomalies related to all these elements when you combine them? And that has been confirmed that it is actually within the central and some parts of the western part of the study area. So in conclusion, this study actually investigated the practicability of using hydrogeochemistry in mineral exploration within the Taquin, which we believe has not been done before. It's just the first that we have tried it and it has worked. And you can see the results, which actually indicated that the water type that is dominant in the area is calcium sodium bicarbonate water type, and which also had some other mixed forms because of the recharge sources we are having in the area. And the principal factors that control the chemistry of the water were actually identified as water-rock interaction, silicate mineral dissolution, and ion exchange reactions. And the study has reported that gold mineralization in the Taquin is directly related to iron oxide formation. Minerals like goethite and hematite, they were identified as the indicator minerals since groundwater shows supersaturation with respect to these minerals. And we will confirm this also with our petrography studies, which we are yet to do. And gold actually formed in an oxic environment with hematite as the dominant mineral. And the multivariate statistics indicated the association of gold with most of the parameters. And this may be due to three factors. One is weathering of the host metal sedimentary rocks, redox reactions in the aquifer, and the mixed sources from which these elements may be coming from. And the associations of the elements may imply that the occurrence of gold in the Taquin is directly associated with secondary dispersion of the underlying host rocks and the oxidation potential of the groundwater. The important pathfinder elements that we identified in this study are iron, nickel, lead, arsenic, and gold. So we are advising our industry partners that when you are exploring in this terrain, these are the iron elements that you should be interested in. Anomalies related to these pathfinder elements are actually restricted to the central, the southwestern, and the northeastern parts of the study area. So based on all these conclusions we've drawn, we recommend that mineral exploration in the Taquin should focus on areas dominated by hematite as the main indicator mineral. And the best mode, except maybe you are dealing with the hydrothermal deposit, which we are yet to work on, the best multi-element association that is related to gold mineralization in the Taquin is iron, nickel, lead, arsenic, and gold. So when you drill and you are getting anomalies related to iron, nickel, lead, arsenic, and the element gold, then there is the possibility of finding gold mineralization in that area. And we recommend that mineral exploration survey should target the central, the southwestern, and northeastern parts of the Takwa area within the Taquin, because these are the areas that have the anomalies. And we also recommend that hydrogeochemical surveys should be added to geochemical exploration strategies in order to help uncover deeply buried deposits. Because when you look at the state, things that have been done in the industry, they use superficial methods, stream sediment sampling, soil sampling, which is not deep enough to unearth buried deposits. So using this would help us, and the method is so easy that you can use any borehole that has been drilled. Your monitoring boreholes can even be used. So I would like to thank you all, but before that, the principal investigator will come in.
So what we are trying to say now is that at least we should be involving hydrogeochemistry and hydrogeological mapping in mineral exploration, because these help us to identify deep and buried gold deposit that you can have with the Takoyan. Thank you very much. We would like to thank the Ghana Chamber of Mines Tertiary Education Fund, for faculty members for financially supporting this project under the auspices of the University of Mines and Technology. Thank you very much, Dr. Ziga. We are done.
Thank you, Prof. This is a very wonderful presentation. It's question time. Dr. Sunkari, if you can still share your screen so that if someone wants to ask a question.
All right.
So question time, kindly show by hand and then I will call you. Yes, Prof. Andy Barton.
Yes, Dr. Sankari, thanks for your presentation. At this stage, do you have any sort of numbers for the indicator elements? You may have the background, and with the background, you have certain amount that may indicate something. And also, how does your study compare with similar studies in other places, like in South Africa, they have deposits similar to that? Do you have the same indicator elements? And how has the what you recommended be useful for further exploration? Thank you.
All right. Thank you so much, Prof. Yeah, so we have threshold values or background values for all the the Pathfinder elements we've identified. After calculating the anomalies, we were able to get the values for each, and that was what we use in actually plotting the map. So if you can see the maps here, the values that we have here, for example, if you have arsenic values ranging from 1.00 to 1.1, then it is an anomaly, which is very good and can be used for exploration. And with respect to comparison with other studies, yes, our study actually resembles that of deposits in the Witwatersrand area in South Africa. They also work on paleoplacer deposits, which is just like the Taquin deposit we are dealing with. So we have similar pathfinders, and it is actually in consanguinity with that. And once it's an ongoing work, we are going to produce a report, and we will do these kind of comparisons. And if we are given the opportunity for getting more funds, we will extend it to other terrains.
Yeah, Dr. Let me mention that I know there are similar deposits in Canada too, you know, which are similar to the one in Wits and then the Taquayan. So any other things you can include that. Thank you.
All right. Thank you so much, Prof.
Please, any other questions for the presenters? All right. Thank you, Dr. Sunkari. You can now share your screen.
All right. Thank you so much, Dr. Ziga.
Our next presenter will be Dr. Eric Thompson Branson. He was supposed to present as the last today, but the second presenter has asked for some time to present as the last. So, Dr. Thompson, please, you can start your presentation.
Okay, thank you very much, Dr. Ziga. My name is Dr. Eric Thompson Branson, a lecturer at the Petroleum and Natural Gas Engineering Department, and currently the School of Postgraduate Examination Officer. So we carried a research on the hybrid technique for pre-split drill and blasting for stable walls of open pit mines. I am the principal investigator. Now, these are my cohort investigators. They all assisted in carrying out this project. Now, this is my presentation outline. We have the problem, we have the introduction, the problem statements, the objectives of then the methods used, conclusion, recommendation, and future works, and the acknowledgement. Now, as part of measures to improve on the quality of teaching the UMaths, the Chamber of Mines introduced a research fund for faculty members, and this program has really helped lecturers to do research in the mining industry. Now, currently, our project focuses on the hybrid technique of pre-split drilling and blasting techniques for open pit mines, which was carried in 2 different mines. Now, we all know that the basic theory of control blasting is to minimize the effect on the final work. Now, this can be done in such a way that we can minimize the explosive energy that is being transmitted to the wall. Now, this can be done through using control blasting techniques such as the line trim, smooth. Then we have the pre-split, which is the most practicable technique. Now, in pre-split design, holes are usually drilled along a single row of excavation line. Then they are blasted prior to production blast. Now, these holes are usually charged with light or explosives which are decoupled from the rock. So we do this in order to minimize the comprehensive failure around the blast holes. Then we have some methods which we can use to assess these pit walls. We have the physical inspection of the smoothness of the pit walls, which we can use to assess whether the walls are satisfactory or unsatisfactory. Now, another problem that we usually face is the borehole deviation, which is also a problem which can affect pre-split drill and blasting. So in the figures below, you can see the figure that we have here below. You can see these are the barrels, the half-cast barrels which are on the face of the pit wall. You can see that most of the holes that were drilled, they were not parallel to the face. So you can see the pre-split effect due to hole deviation, which is here. Then we have some situations where we have the crest is lost. You can see we can have some protruding walls, which is here, which you can also see some of the barrels. You can see some of the crest here is even lost. Then we have another one over here, which is also shown in the diagram over here. Then all this has contributed to the loss of the crest, and some of these will require redress, which will also incur costs for the company. So basically, we did a wall assessment. So you can see in the diagram over here, you can see that in this diagram, there's no visible barrels which is on the wall. You can see, so this is the problem which is currently at the site over there. Now, in order to assess this, we have some methods which are used to what? So you can see here that we have an example which is here. If these walls are not being monitored, we can have a situation like this where we have the crest damage or the toe deviations, which can result in the total shut of the mine. As I've already said, we can also have some drilling problems if, let's say, we have misaligned coloring or inconsistent with drill operations, which can also affect the operations in the mine. Now, our main research objective are to introduce an optimum of time delay into the press plate drilling and blasting, then to geotechnically identify failure mechanism in an open pit, then to also develop a locally made short exploder with the continuity tester for surface and underground blasting. Now, why do we do these press plates? We do these press plates in order to achieve catch beams for the safety of personnel, then high wall stability. Then we want to also minimize the crest damages and also reduce vibration. Now, basically, this is a typical example of a press plate design. So you can see in the diagram over here, we have the beam, we have the first bench. So we drill it at an angle of 70 degrees, 12 meters. Then we can combine the second and the third bench, which will be what straight hole, which is also drilled here. So usually the picture that I've already showed, when we drill this, we have problem with hole deviation at the site. So you can see in a typical mining environment, we have our production holes, which are here. Then we have our buffer holes, which are also drilled in order to minimize the energy that is being transmitted to the wall. Then we have our single row of press plate holes, which are also drilled here. Usually we drill it at 114 millimeters. Then we have the buffer holes 165. And the production. Now, the basic cartridge that is usually used in this press, which is already, you can see in the diagram here, is gets the toe at the bottom over there. So it can work in both wet and dry conditions. Then in the press plates, operations can be used in the press plate design and blasting. So we suggested that press plate design auditing should be done. Then the angle adjustment information. And we should also have a press plate drilling team, which can also be used to improve operations. And the use of, then the hole spacing currently 5. Yes, that was what is used, so 2.5. So we can also optimize this hole spacing. Then we also have highly jointed rocks. If you have highly jointed rocks, the spacing, you should also look at the spacing, which is that. Then we can also use some of these drill rigs, such as a DTH, in order to minimize these deviations. Now, how do we assess this press plate, the assessment? We have a common tool which is known as the half-cast factor, which is used to assess the press plate barrels, which are shown on the pit walls. So you can see in the diagram we have here, these are the barrels which are shown on the wall. You can see this and improved press plate. You can see the spacing between them. So we are able to calculate this half barrel. So I calculated one. See that we are having 91.67, which is showing a good or improved press plate for the site. Now, at this point, I'll hand over to one of my co-PI to continue with the slope failures analysis.
Good day to you all, distinguished panel and fellow participants. I am in the person of Alvin Kwatin Kobi and will be presenting on the topic, slope stability analysis. So in Ghana, the most commonly preferred method of gold extraction is the open pit method. This is due to the notable advantages that open pit mines have over the underground mines. Some of the advantages include reduced cost and also faster production rates. But with its advantages comes some disadvantages, which example being slope instabilities. So the cost of remediation of failed slopes can be quite high, and it is therefore of high importance to actually carry out analysis in order to prevent these failures from occurring. So Flag3D software was basically used for the analysis, and Flag3D is also an explicit finite difference program that is used to study the mechanical behavior of a continuous three-dimensional medium as it reaches equilibrium or steady plastic flow. So in order to perform the analysis, a 3D model was created. A DXF file was first of all created in SEPAC, and then it was imported into Flag3D building block pane. So the DXF file together with the building block pane was used to actually create a 3D representation of the pit under consideration. So this is the DXF file that was created in SEPAC as shown in figure 1. And also, as seen in figure 2, the control point of the building block pane of the Flag3D was used to map the surface of the building block model to match with the DXF file that was imported to create a realistic or more accurate impression of the pit under consideration. Okay, so after the model was created, it was time for us to actually assign or attribute geologies or characterize the pit with geologies. And the major geologies which were considered are the metavolcanics, the metasediments, and the graphitic mylonite. And due to, or because of the geological set of the mine, the Mole-Coulomb constitutive model was used for the analysis. So this is basically a stratigraphic section of the geological unit as sourced from CABA 2013. Okay, so after the geology was characterized, this is the results as seen in figure 5. So in order to actually calculate or verify where there will be likely failures in the pit, the strength reduction technique was utilized. And with the strength reduction technique, it basically reduces some properties of the zones, properties we specified for the model. It reduces the properties like cohesion and also the frictional strength of the frictional angle of the 3D model. So for Flag3D, it basically uses commands, just like scripting of codes in Python and other languages. Flag3D basically operates using commands. So a data file of command was created in order to solve the model in the first case to a convergent state or a state of equilibrium. And another data file of codes was also created to actually solve the factor of safety of the pit under consideration. So below is a summary of basically the methods that were used in order to carry out the analysis. So a 3D model of the pit was created and it was calibrated to a reasonable extent. And also zone properties and materials were assigned to the model. And because groundwater has an effect on the stability of the slope, groundwater conditions were also imported into the model. And also boundary conditions were applied to all the northern faces, the south faces, and the other faces of the model. And after, the factor of safety was computed for. And finally, the interpretation of the results. Okay, so the data file was created to actually solve the model to a converged state. And as seen in figure 7, that is the model at its equilibrium state. And this equilibrium state was then used to actually calculate the factor of safety of the pit. So for factor of safety calculations, basically Flag3D computes a characteristic number of steps. These are the steps in which the model would reach equilibrium or come back to a converged state. So after the characteristic number of steps was calculated for, a first stable state, a first stable FOS was calculated for. And after, a first unstable state was also calculated for. And Flag3D basically utilized these two states in order to compute the more accurate value or more accurate FOS of the slope. Okay, so as I stated earlier, groundwater has a significant effect on the stability of slope, and they basically change the stress state of the rock, the surrounding rock of the pit, and also increased pore pressure results in a reduction in the shear strength of the rock units in the pit. So groundwater also showed a significant effect on the stability. And also fault areas they were likely to create paths for entrance of groundwater into the pits. And I'll see in the video on the left, we can see seepage of groundwater into the pit model. And I'll show in figure 8, we can see the pore pressure gradient of the pits was simulated for. Okay, so this is a pit as a result of improper or groundwater seepage. We can see that the pit is flooded. This was due to an unfunctioning pump at the mine site, which caused this flooding that we see. Okay, so after the strength reduction was used to actually calculate the factor of safety, a displacement map was created. And the displacement map of the model was compared to the actual displacement that occurred at the pits under consideration. So as seen in figure 9 is the actual failure that occurred in the pits. And as seen in figure 10, we can see, as seen in figure 9, this is the failure surface. And as seen in figure 10, this is also what Flag 3D predicted. And we can see that from comparison, Flag 3D was able to predict the instability or where there will be likely failure to a reasonable extent. Okay, so after the factor of safety was computed for, it was compared to a failure criteria to identify the type of failure that was occurring at the site. So the criteria is given below. And as a stability criteria of the factor of safety was actually 1.3 or more. The factor of safety of the slope has to be greater or equal to 1.3. Okay, so this is basically a section view, a 2D section view as shown in figure 11. And the factor of safety that was computed for was 1.8. So comparing the factor of safety that was attained, we can see that the failure that was occurring in the pit was actually a circular failure, as shown in figure 13. Okay, so Flag 3D was basically able to predict to a reasonable extent the failure that occurred in the actual pit. And also the zone pore pressures were calculated for. And with the zone pore pressure, this will help the engineers to better design, create informed or take informed decisions to create sumps at the pits where they can use the sumps to actually dewater the groundwater that will be seeping into the pit floor. So if
Okay, so we move to the other part of our work. Usually, that's the short exploder and the continuity circuit tester, which is used usually when we are at UMAT over here. We'll be here, then we hear some vibration. Yes, today you are going to see the tool that is used to give the initiation system. So usually the old system of initiation is the plain detonator and the safety fuse that is usually used. And this, it has a high accident potential. Then if you want a better breakage and high productivity, yes, and it can also cause problem to blastmen. So you have to linger around the face in order to what? In order to light all these safety fuels. But we have gone past that stage. But if you go to most of the areas where galamsey is still going on, some of this initiation system is still currently being used. So we have the safety fuse, which is also here. You can see how it's burning. Then we have this thing you can see in the diagram over here. This is a typical rock that we have the safety fuse that is being used. Then you can see the detonation that is taking place when it's being used. You can hear the sound. So basically, this is what is being used. Then, with our short exploder, this is the first trial we made, and we failed. Yes, we made this short exploder and we failed. It didn't work. When we sent it for trial, it didn't work. So this was our first setup. We have to go back to the drawing board again and come out with another design. So basically, in order to test our device to show that whether it is working, we were able to prepare a black powder where we use sulfur. Yes, sulfur, we bought sulfur at the market. You can see in the diagram here, this is our charcoal, this is the sulfur. Then we got potassium nitrate from Takwa Secondary School. They also assisted us. So we were able to prepare this powder over here, which we use to test our device. So you can see the specification of our device. We have the nominal hot firing voltage. We have the nominal output energy, which is given there. Then it has a rechargeable battery of 8 hours, which is also given there. Now you can see this is the trial with the gunpowder we prepared at the lab. We are also grateful to the mineral lab. We were able to carry out that research over there. So you can see this is the short exploder that we have been able to develop locally. So you can see that this is the first trial that we did with the exploder. So now you can see this is our continuity circuit tester. Usually in surface mine, we have the connectors. If they connect all the holes, we need to test for continuity. So this is the device that is here. This is the device you'll be able to produce, which was used in the mine for the testing, for the circuit testing. Now we have a typical underground mine. We have the ring design, which is used. We have the boreholes here with the delays at the top. So this is the ring design, which was done in data mine. So you can see our device was first used for the first underground portal blast at the mine. So we can see the fragmentation, which is here. So they are opening a new portal, and our short exploder was used in order to carry this first blast over here. Now, this is the mine site where the drilling operation is. This is the drilling cabin. We have the console, which is here. Then we have some causes of hole deviations, which are also enumerated over here. Yeah, so basically, we were also able to model the rig. We were also able to model the rig. You can see this is an ongoing project. We are still on it. We were able to model the rig at the drill site. So because we know that these borehole deviations, they can have effects on the mining pit wall. So it's currently an ongoing project. You can see this is the rig that we have here. You can see the drill string going down, making a hole. You can see it in the video over here. Then we also have a situation where we simulated the hole deviation. So you can see the hole deviation. You can see this is the formation. This is the formation. So you can see we were able to model it. You can see the deviation that is taking place underground. So you can see. So we have the trap. So this what you have from discontinuity in the formation, you can see initial images that I showed. Then we move on to the testing of our device. You can see the engineers at the site. So we have our circuit, our continuity tester. So you can see in the diagram, the engineers are testing the continuity tester that we develop at UMAT here. So you can see it's working over there. So you can see that it's working, the engineer, so you can see it's testing it. It's testing for continuity. to ensure that all the surface is connected. So this is the locally product that was produced here in UMAT. So you can see the engineer giving the shot. So you can hear the sound. Yeah, the shot has been given. So you can see it over there. So the device is actually working over here. Okay, so this is another blast that was also taking place. This is an AEL guy. He wants to test the product from UMAT, whether it's really working. So the engineers gave it to him to try. So you can see that the engineers themselves, they are confirming that our device is faster for the blast. So you can hear it. You can hear them speaking. They are speaking the local dialect. So that's it. And you can see the mock power after the blast, which is also given over here. Now, we did everything from the scratch. You can see the engineers at the side, they opened the one that they bought. And this has been what? Sealed it or been concealed. You can't break it. It's a tough plastic, which you can't do. So we designed all our circuit, we designed everything from the scratch. So you can see it with the evidence over here. You can't open it and say we have copied or this thing. So this is currently what they use. Then we have been able to also come out with our own. Now, this is also very interesting. After we produced the short exploder, we now went on to what cost-saving effects. Now, you realize that in the mines, they use harness wire. This is the harness wire, which is being used for firing. So we came with we have the 4 power core power cable, which is here, which we also recommended for the mines. Because usually this one, after every blast, usually fly rods and other moving equipment can destroy the firing lines. So with this one, we can have a good firing line. So you can see the engineers at the site which are using the core power cable that we have recorded. So our device has been working for the past months. When it comes to drilling and blasting, we have to also look at the environmental assessment. And according to the LI in Ghana, we have we have ground vibration, which should that of the air blast, which is what 117 decibel. So these are the regulations which are permissible in the mines over here. Now you could see this is a data that is showing the blast use. You can see compared to the threshold that is given here, you can see it over here. This is the air over pressure. You can see that it falls within the requirement. Then you can see the ground vibration, which is also here, which also meets the requirement for the various locations. Then we compare this to overseas blasting vibrations, which is also here, UK, United States, Japan. We also compared it to this, and you can see that what it has met the requirements. Now, another thing we also did, our aim towards that we want to save costs because drilling comes with cost. That is one of our aims. So you can see that in the month of July, so we have this, if I go back, you can see that we have this wire, we have this one, which is the we have 1,200 meters of the harness wire, which is going to be used. Then this is the actual, so they actually use this one. Then we have for the month of August, you can see that in the month when we recommended the 4 core power cable, you can see that they use this, if this is the forecast for the harness wire, then you can see that where we have that was where they use the 4 core power cable, which was used. Now we did some little estimation to see how we are saving costs for the company. So a forecast was done with the 1,200, which is here in the month of July. Now, per meter of that wire, that harness wire is $0.56. So if you multiply this, this is what you are getting over here. Then in the month of August, which is this, if this is the forecast, this is the actual forecast, you can see it here. So they were supposed to pay what? $1,344. So you can see from the estimation over here that in the month of July, no cost was saved. But when we recommended the 4-core power cable, you can see that this is the amount that the company has saved. You have saved the company. Now, we also went further to do it for another mine where they do 28 shots in a month. So you can see this is the forecast if they are supposed to use harness wire. You can see over here, they use what for the 28 shots, they use 1120 of the harness wire. Then you can see this is the cost. This is the cost. Now, if we use the 4-core power cable that we recommended, you can see that this is the cost that was incurred over here. Okay. So now when we take this, even when you take the difference from this, you can see the cost that is saved. So you can see that in effect, we have saved about $5,132 for the company. Now, in terms of cedis, this is the amount that is given over here, which is about 58,000 Ghana cedis. In terms of the test circuit continuity, which was procured by the company, the one we manufactured, you can see that 3 of them, the unit price is $718. Now they bought 3 of them, which is giving you this amount. So now they bought 3 of the short exploder to which we did at UMAT over here. 3 of them is also giving you this amount of dollars, which is here. So when you sum up this, they spent $10,674 on this blasting device. Now let's see something interesting over here. So this is the product from AIC, which was procured. Now, if you look at our own that we did, you can see over here that this was the total cost that we did this. So it's $489. Now, out of this, you can see that this is the total amount in cedis that was used. Now, compared to this is in dollars. The one here is in dollars, which is $10,674, compared to this one, which is $489.81. Now, you can see over here that this is converted into cedis. This is the cedi amount over here. This is the cedi amount, which is 5,608. Now, when you do this computation, you realize that the cost that we have saved, you subtract this 10,000 from the cost that's of our device. So we are saving the company about $10,184. When you translate this into Ghana cedis, this is the equivalent Ghana cedis. This is the amount that we are saving for the company. So now with that one, we were also able to go ahead and do some publication. So we have currently sent one paper, and the paper has been resubmitted for publication. So in conclusion, I will say that an optimum timing sequence should be introduced into pre-split blasting, which is currently going on. Then our research has also been able to identify failure mechanisms in the OPP.